Okay, here we go. So last time we were almost done with section 7.2. What we hadn't covered was, in fact, just basically some supplemental stuff. It's not really in the book. It's not critical for any of the exercises. That's where I went ahead and assigned 7.2 for yesterday's class meeting. So, in other words, part of the homework set due this weekend. So a quick reminder of where we were so we can finish up with this section and move along. I had made this observation that even though vector line integrals, which is a result of a game played with these players right here, and vector surface integrals, likewise, these are the players in that game, they have a lot in common structurally. Now, of course, they're dimensionally different. Of course. They compute different, they're motivated by different physical quantities. Lots of things are different. But structurally they have a lot in common. And I pointed this out by kind of color coding. And you see, so for example, the velocity vector and the capital N vector play analogous roles. They're derivatives, effectively, of their corresponding parameterizations. And then look how analogously are the roles that they play in the resulting algebra. And then likewise for all of the different objects, every player on the left, there is a analogous corresponding player on the right. And I think this comes across really well when you color code. I went ahead and took the liberty of reproducing this in advance for today's lecture. You color code everything in the diagrams and then correspondingly in the equations, and the colors are, it can almost kind of copy paste the coloring from the left and superimpose it over the right. It's a perfect analogy, right? Very, very strongly analogous. Okay, and that's where we ended last time. The only thing I wanted to add to that is that you can keep going, as it were. Here's a bunch of different versions. Let me try that again. Here's a bunch of different versions of what vector line integrals look like, different ways to write vector line integrals. Here, likewise, vector surface integrals. And notice the color coding analogy continues. Again, I took the liberty of color coding in advance, but you see the role that velocity plays, the role that capital N plays. It's the same role, right? And likewise, the ds scalar, d capital S scalar, analogous, and et cetera, et cetera. So I think this is a really worthwhile observation. Again, all of this is a consequence of the fact that ultimately a vector line integral is an integral of a differential form, and a vector surface integral is an integral of a differential form. Different kind of differential form, but still a differential form and still also an integral. And so they act similarly because ultimately they are the same thing. Just different applications. Okay, that's all I wanted to say on that. And with that done, we're going to move along now to 7.3. This is another one of these massive sections. Kind of like what was it, 5.5? I think it was. It was huge. It took us like 3 or 4 class meetings to get through. Same thing here. There's a ton of stuff to say about Stokes' theorem. And there's a ton of stuff to say about Gauss's theorem. And for some reason, the author felt it necessary to put them both in the same section. I don't really know why that is. But anyway, it's fine, whatever. That's just organization. The book does Stokes' theorem first. I get that. But and I believe most other multivariable calculus authors put Gauss's theorem first, and there's good reasons for that as well. So I'm going to do it the way I want to. We're going to start with Gauss's theorem. Okay. All right, now what I want you all to keep in mind as we go through this is that this is highly analogous to Green's theorem. Then again, the fundamental theorem of line integrals is also highly analogous to Green's theorem. The fundamental theorem of calculus is everything's highly analogous to everything else in some sense. But what you're going to most know, the connection I want to most focus on is the relationship between Gauss's theorem and Green's theorem. Now they take place in different dimensions. We're in R3 for Gauss's theorem. Green's theorem is strictly in R2. So, yeah, dimensionally different. They're going to be computing different things. We'll get to that in a minute. Of course, full recognition of the differences, but even though they're computing different things in a different world, strong analogies. Real quick, just so you can kind of see this coming, the very first thing we talked about when we did Green's theorem is we talked about what does boundary mean. Boundary has to imply an orientation, and we talked about the convention for that, blah, blah, blah. And then we talked about what it means to have an accumulating quantity. Well, that's going to be our next thing here as well. And that when you have an accumulating quantity, you can talk about the accumulating quantity as a kind of a stuff that is literally distributed throughout the interior, even if it doesn't sound like it. And that there is a corresponding notion of density. You can go back to our 6.2, I guess it was, notes, and the subheadings are in the exact same order as we're doing here. So I want to, just broad strokes point that out before we get into the details. And now here, back to the details. Okay, so looking at a solid region called R in R3. Highlighted in gray here. I'm going to further highlight it in green for focus purposes. There's our solid region R. It's a weird solid region. It's got an air bubble inside of it, right? So it's solid in the sense that it's three-dimensional, but it's not 100% solid all the way through. We're going to talk about the boundary surface. From the picture, not hard to persuade yourself that the boundary surface consists of these two surfaces like that. Hope that's believable. Note that there are the two chunks of the boundary. That's just the way this particular what would I call it? I mean, I keep trying to come up with something better. Oh, you know what it's kind of like? It's kind of like a cantaloupe, isn't it? Anyway, not that it matters, but anyway. Okay, so question. When we say boundary, and with the understanding that boundary has to give us an orientation, we're going to be computing oriented quantities on this boundary. What is the orientation on a boundary of a three-dimensional solid? And again, the answer is going to be arbitrary. You might say it was arbitrary 150 years ago when these ideas first started getting tossed around. But at this point, the convention's highly standard. And so, yeah, it was arbitrary, but at this point, it's just it's a standard, and we have to stick with the standard. Here's the standard away from the solid. So, for example, look at a point like this point right there. That's on what you might call the outer portion of the boundary, away from the solid. Like that. Is everybody good? Now, I want to distinguish between away from the solid, which this is, and outward, which this, I guess, also is. We don't want to conflate these two concepts. They're not quite the same. Let's see, for comparison purposes, let's say this point down here. Keep in mind, the solid is in green. This is where the solid is, down here in green. So away from the solid is like that. That's away from the solid. But you wouldn't want to call that outward. If anything, that's inward. Right, so again, there are, just like with Green's theorem, you remember I kind of warned you all off of this idea that, it's always counterclockwise. Not really. That's the simplified, most of the time, I guess, answer to the question, but it's not always right, and there was a different convention there. So likewise, beware of the concept of boundaries being outward. It's not always outward. It is often outward. But what it always is away from the solid and into the nothingness that the boundary separates it from. Okay, how are we doing? Is everybody with me? All right. Okay. So let's talk about accumulation. Green's theorem was about boundary circulation. That is not what Gauss's theorem is about. Gauss's theorem is about a different thing. It's about boundary flux. So, different thing. I claim, though, that it does accumulate. I want to justify for y'all why boundary flux is an accumulating quantity. Ultimately, by the way, this is the nugget, this is the seed, the kernel on the inside. This is what makes it all work. Right here, this argument that boundary flux accumulates. Okay, that the whole is the sum of the parts when you're talking about boundary flux. This is what makes it all work. So, that said, what does boundary flux look like? Keep in mind, we're talking about for a solid, so we want to start by thinking about this whole solid. Boundary flux. Oh, you know what? Let me do it like this. I'm going to try to anticipate. There we go. There's the boundary. Here's the, keep in mind our convention away from the solid, which in this case is also outward, as it turns out. And there we go, in purple, a sort of a representation of the boundary flux for the whole. Okay, now let's talk about the parts. Let's look at the left side. You know, once I chop this thing down the middle, there's the left side of the solid. What is the boundary flux on the left side? Well, there's this piece of the boundary, outward. And then there's this piece of the boundary, also outward. Now let's get the solid out of the way. So we have kind of two chunks, if you will, for the R1, for this green solid. The boundary pieces are there and outward, well, away from the solid on all of those faces. Everybody all right? Same deal now with the right side, this R2 thing. Right? So there's kind of this piece here, oriented away from R2. And then there's kind of this here, if you will, oriented again away from R2. So the blue figure there represents boundary flux for R2. Okay, so the question before us is green plus blue equal to purple? Right? And now, some of it is pretty clear that, if you look over here, this stuff over here, the purple, the left side of the purple there, the left side of the green, they have the exact same surface with the exact same orientation. These pieces here cancel. On the right side, if you will, the blue surface, the remaining purple surface, well, again, exact same surface, oriented exact same way. All of this cancels. And you see what remains is just this one shared face. And we're computing flux through that shared face twice. So tempting to say that it doesn't accumulate, it's already failed. I see there is a difference between the whole and the sum of the parts. This is the difference, but the thing is, this difference is the same flux computed twice, but with opposite orientations, and they cancel. Now, this is really, really analogous to what we saw in section 6.2 when we did the two-dimensional divergence theorem. And I think it's a healthy exercise to flip back in your notes to where we talked about the 2D divergence theorem, and we drew a picture that's really, really similar to this, right? But in a different way, there is also a very, very similar picture when you're talking about Green's theorem. It still remains that there is a shared piece that counts twice with opposite orientations. It's just that instead of opposite directions through the face, it was opposite directions along the curve. Still opposite, still cancel. Okay, so this is kind of a brand new picture, and it's also kind of our third or fourth time to see morally equivalent, the same picture. So, nice punchline. Boundary flux is an accumulating quantity. How do we feel about this? Everybody okay? Okay. All right. Well, it's all downhill from here. Everything follows from this. Because it's an accumulating quantity, I claim you can treat it like a kind of a stuff. I claim any accumulating quantity you can treat as a stuff kind of distributed over the interior. Now, it doesn't feel like it when you first look at the term boundary flux. We're accustomed to thinking of flux as being computed on the surface, which is the boundary at this point. And this is reinforced by it explicitly saying boundary flux. So the verbiage itself is pointing us toward thinking of it as being on the boundary. I want to encourage y'all to try to disregard those suggestions in terms of how you actually think about boundary flux. I want to encourage you to think of boundary flux, again, as actually being distributed over the interior in the same way that mass is distributed over the interior, or population of mosquitoes flying around inside of a whatever. It's a stuff that exists and is distributed throughout the interior. Okay, now I know that sounds weird. So now here's my recent take on how to persuade you to think about it that way. I'm going to talk through the accumulation feature of boundary flux, but I'm going to do it without saying the word boundary flux, because again, the problem is the language. This just linguistically is pushing us in the wrong direction to want to think about it as being on the boundary. So I'm going to, instead of boundary flux, I'm not going to say boundary flux. I'm going to say blah, blah, just as a filler, right? And now I'm going to say a bunch of stuff about it without, again, the misdirections from the language. Okay, so we've established that blah, blah is an accumulating quantity. Right? And what that means is the amount of blah, blah for this region here is equal to the blah, blah for this region plus the blah, blah for this region, right? So the blah, blah for purple is equal to the blah, blah for green plus the blah, blah for blue. And that makes it sound like, and I believe it's very reasonable to think of it as, that the blah, blah is distributed over the interior. We can take this multiple steps forward. If I look at the blah, blah on a given piece, and if I add that up over all of the pieces, that make up that solid, then the result, the grand total of all of those little purple pieces of blah blah is that I get the blah blah for the whole. Doesn't that really sound like, and it behaves like, and it just smacks of stuff distributed throughout the interior, as if it is a physical, concrete kind of material almost. If it were a physical concrete material, it would behave exactly like this. So anyway, now, the language, boundary flux, is directing us in different intuition. Please try to ignore that. I think it's counterproductive. Okay, so we have a stuff, like a mass-like kind of a stuff. And with that in mind, I want to talk about how much of that stuff there is per unit size. So let me remind you, just for comparison purposes, an old concept, the idea here of mass density. Mass is an accumulating quantity. The whole is the sum of the parts. And mass density means how much of that accumulating quantity called mass is there per unit volume. And so I'll be looking at literally how much mass is inside of there. And mass density is what you multiply by volume to get mass. Okay, so that's old news. Now I'm going to do the exact same thing. Talking about now a different accumulating quantity. Now we're going to talk about flux density. Well, okay, now flux, still an accumulating quantity. Still something that we think of as a stuff-like quantity that is distributed over the interior. And I can talk about how much of that stuff there is in any given little region, which I've drawn two-dimensionally here just for kind of artistic reasons. But thinking of it three-dimensionally, of course. So, well, stuff per unit volume is what we mean by density. And so in the same way that mass per unit volume is mass density, likewise flux per unit volume is flux density. Everybody okay with that? Seem like a reasonable analogy? Right, if I were counting mosquitoes, it'd be mosquito density. Okay. And I can make this argument again because we've agreed above that that this quantity flux is an accumulating quantity, can be thought of as having locations and distributions throughout the interior. That's why this makes sense. Okay, now then the question becomes this thing, flux density. What is it? How do I compute it? What's the formula? There is an argument that you can make. I'm not going to go through it in this course. You're not expected to know this in this course. It's just got a certain amount of tedium in it. It would take up a certain amount of time, and it's ultimately just kind of details. But here's the answer, the punchline that you may use at your leisure. Flux density is this formula right here for a given vector field PQR, as usual. This formula, of course, we recognize that we've seen that previously. We called it divergence. We had these notations for it. All of these are representing what I encourage you to fundamentally think of as being flux density. Okay. Everybody okay with that? All right. Just a FYI, some of the terms that I use in this course, I've confessed as we've gone along, are terms that I like to encourage because I think they're instructive. I think that they take your intuitions in the right direction, but they're not necessarily particularly common. I think the biggest example of this is thinking of the derivative as change density, right? That was a weird one. Nobody's ever heard of that outside of, I don't know. I don't want to speak too broadly. But anyway, it's not standard single variable calculus talk. For sure. But I want to be clear, that's not what's going on here. Flux density is an extremely common term. Now, the math word for this is divergence, and in math context, you'll probably hear the term divergence more than you'll hear the term flux density. But for whatever it's worth, in my physics classes when I was an undergrad, I heard the term flux density from my professors more than I heard the term divergence. It's an extremely common term, and I am a big proponent of this idea. It just communicates what the stuff is. Again, you can talk about divergence, and you can write down a formula for it, but the way that you think about it, what is divergence? How do I visualize it? What is it good for? Where does it come from? Is this right here? It's the fact that it gives you flux per unit volume, right? Which is kind of implicitly, the subtext is that flux is an accumulating quantity. All that's wrapped up inside of this one lovely term, flux density. So I love it. I'm a big fan. I encourage y'all to think of divergence that way. And be prepared, by the way, that you're going to hear that in your future. Well, for those of you who are engineers, apologies. I know not everyone is, but I believe the majority of the students in this class are. You're going to hear the term flux density plenty. All right. So, as with all of our other densities, flux density tells you how much of what you're measuring as a whole is actually happening at given locations in the interior. Now let me remind you, back in chapter 6, I did this little aside where I pointed out that you can think of the fundamental theorem of calculus as an accumulation theorem. Change accumulates. The whole is the sum of the parts. And as such, as I recently referenced, you can think of the derivative as being change density. It is a corresponding density. And more than that, it therefore kind of tells you where the stuff is. Right? So if you want to know, for example, you've got a total quantity of 9, this quantity called change, how the total quantity of change that there is on this function between 0 and 3 is 9. That's the total amount. Is there more of that happening at the point 2, or is that more of that happening at the point 1? Where is there more change? Okay, well, yeah, let's get aside from the obvious quibble is that 0 change happens at a point. Okay, fine, right, but you know what I mean when I say how much change is happening at a given point. I mean per unit size of the domain, how much is the function changing? Obviously, we mean per dx, right? And the derivative not only tells us the answer to that question, but it intuitively tells us, right? The derivative is telling you how much of the change is happening. You can see that there's more change happening at the point 2 and less change happening at the point 1. And again, abusive language, I say at the point, what I mean is in intervals near the point and per unit size and all that, of course, But anyway, the point is that the density tells you where the stuff is coming from or where the stuff is in the interior. And I pointed out that you can likewise do the same with our other densities. For circulation, Green's operator is the density. And so if you're interested, between these 2 points, 3, 3 and 2, 4, and we did these examples before, so I'm rushing through this. If you want to know where there's more circulation happening between these 2 points, look and see where Green's operator is greater. That's the one where more stuff is happening. Right? And then likewise, analogously, two-dimensional divergence is two-dimensional flux density. That tells you between these 2 points, right? But given these 2 candidates, between them, where between these is the most flux coming from? Well, the one where the divergence is greater is the one where more of the flux is coming from. So, with all of that in mind, same interpretation. Now let's look at three-dimensional divergence. Three-dimensional flux. Got a vector field. It's creating flux through the boundary of some large solid. Doesn't really matter. Where is there more flux created? Is it this point or is it this point? And well, we look at flux density. Flux density points to where the flux is / where the flux is coming from. And you see it's greater at, between these 2 points, it's greater at B. So there's more flux being created at B. In the same way that derivative tells you how much the function's changing, divergence tells you how much how much flux there is there at that point. Okay. All right, we're ready to put it all together now. Here we go. We've got all these ideas already worked out. We've talked about flux as being a quantity of interest. Boundary flux, mind you, right? Only boundary flux. Everything we're talking about here is boundary flux. So it's an object of interest. The next observation we made is that it is an accumulating quantity. The whole is the sum of the parts. The boundary flux on a whole solid is the sum over all of the pieces of the boundary fluxes on those individual little pieces. And again, that's just chop it up, add it up. The whole is the sum of the parts. That's what it means to be an accumulating quantity, which boundary flux is. And then, density is the thing that allows us to make sense out of how to relate that to volume. Flux density, flux per unit volume, is the thing you multiply by volume to get flux. And all of these ideas having fit together, notice we have our result that if you have a boundary flux aka a boundary vector surface integral. You can compute that with a triple integral over the solid of the divergence of the original vector field. And this is Gauss's divergence theorem. Yeah. Everybody see how these pieces fit together there? Any questions? Okay. All right, now I want to remind you all of our accumulation theorems. I like to call these accumulations. By the way, let's pause and take stock for just a second. Fundamental theorem of calculus, fundamental theorem of line integrals, arguably two versions of the fundamental theorem of line integrals, 2D and 3D. Green's theorem, the two-dimensional divergence theorem, and now Gauss's divergence theorem. So this is our sixth example, depending on how you count. Our sixth example of looking at an accumulating quantity. Once you realize that it's an accumulation, pointing out that the whole is the sum of the parts, and then writing out the corresponding notion of density, you always get theorems that look of this sort, right? And this is our sixth example, by my count, of that kind of a thing. So anyway, as I was saying, so all of these accumulation theorems, all six of the theorems we've seen so far, they all have a catch. There's an asterisk. You can only use it if certain conditions are met. The asterisk, the catch on Gauss's divergence theorem is it's only for boundaries. And, reminder, when we were looking at the accumulation feature of flux, we were specifically talking about the boundary fluxes specifically. So that is a catch. Very, very importantly, you cannot apply Gauss's divergence theorem if your surface isn't a boundary. It's just not a thing. Gauss's divergence theorem just doesn't address the matter at all. Right? So you will get a catastrophically wrong answer if you try to apply the divergence theorem to a flux integral that's not a boundary. There is no divergence theorem at all. It does not make any sense. Again, it's not just that you're going to get a wrong answer. It's that it doesn't make any sense. It's not a thing at all. So please, very, very careful heads up on that. How are we doing? Is everybody comfortable with the catch here? Okay. All right. Let's see an example. All right, we have here a question to compute a flux. Got a vector field given. We've got a domain S here given. Inward-oriented unit sphere. Got to compute a flux. It's tempting to want to use our brand new divergence theorem, and we can't. Again, why? Well, the rule is, we just got through dwelling on this a second ago, if you're going to compute a flux and you want to use the divergence theorem, the surface has to be a boundary. Now let's look very carefully at our surface here and ask, is our surface a boundary? Well, let's see here. The inward-oriented unit sphere, here's the unit sphere. Inward-oriented means like that. Is that a boundary? No, it's not. Boundaries are oriented away from the solid. This is oriented into the solid. So we lose. Everybody on board? Everybody see the problem? Big problem. You cannot apply Gauss's divergence theorem as written here. Okay, the good news. There is a closely related surface. Same underlying surface, just oriented outward instead of inward. Let me say that differently. Oriented opposite of the original blue surface S. And that one is a boundary, no problem. It's the boundary of, well, of course, this interior thing there. Oh, and now my blue looks green. That's not good. Let me fix that. Yeah, so my blue surface is like that. Not a boundary, but the green surface is a boundary. Everybody okay? So we like the green surface. We've been asked about the blue surface. We like the green surface. I'm going to try to rephrase the question about the blue surface to instead be about the green surface. And here's the, of course, way to do it. They are oriented oppositely. And so the integral we were asked about, the blue integral, is just the negative of the green integral. Everybody happy? And that's good news because, of course, the green integral is a boundary. And we love boundaries because we have theorems for boundaries. Okay, real easy mistake to make. Don't forget that minus sign. A lot of students mistakenly think, don't worry about it, it's just a sign error. Not so. The way we look at, and keep in mind, it's not about answers. I cannot emphasize this enough. Don't get distracted by whether or not your answer is correct or how close your answer is to correct. It's not the point. Right, we're looking at the reasoning and what can we tell from the reasoning that you've communicated on your paper that you understood about the problem, and how important are those ideas to the legitimate solution to the problem. Well, orientation is a really big deal. Right? It's a sophisticated concept. It's something we've spent a bunch of time on. And it boils down to just a minus sign, but that, again, that's in terms of the answer. As a concept, it remains. It's an important, sophisticated, significant part of the tools in play. So that's not a sign. If you forget this is not a sign error. This is an important conceptual error. And probably on a 20-point question, that's several points. I don't want to nail myself down, but I wouldn't be surprised if it was 4 points, something like that. It's a big deal. So please be very, very careful with orientations. They do matter. And that in mind, let's move it along. We've, after all this discussion, gotten it down to this integral. The domain is a boundary. That's what the divergence theorem is good for. It allows me to turn boundary flux integrals into triple integrals of divergence. And so there we go. There's where we invoke Gauss's theorem. Everybody okay? Okay. All right. All right, now a couple of details I want to talk through. It's kind of all over but the Chapter 5 aspect of things. But there are some interesting Chapter 5 things here. Well, I guess technically I have to compute the divergence here. Don't forget to make sure you can do this. The x partial of the first coordinate gives me the 3, the y partial of the second coordinate. A lot of good news happens there. A lot of ugly disappears there in taking that y partial of the second coordinate. And then, of course, there's the third coordinate whose z partial is just 0, so that goes away. And we end up with a really convenient formula there for divergence. That's nice. This integral, how to compute that integral, you could technically do this with spherical coordinates. After all, your domain is a ball. We love balls and spherical coordinates. They fit together perfectly. You could do that, but there would still be some trig in there. It's still kind of a pain. Doable, kind of a pain. The nice trick here is to recognize that while this function here is neither constant nor odd, if I break it up into pieces, that is constant and that is odd. This is a little weird thing that happens sometimes, and I've seen this a billion times in undergraduate, again, physics classes, cranking out integrals. That it's just tremendous benefit sometimes to breaking it up into separate pieces and use cool constants tools for the constant terms. Use cool symmetry tools for your symmetric terms. And then the total effort's a lot less. And you can see this works out as an easy geometry problem as a result. Everybody happy? Okay. All right. I do want to make sure that everybody's good with this. Make sure that you can think through those details. What is the appropriate plane? for example, over which we're making a symmetry argument? Are we sure that the domain is symmetric over that plane? What is the formula for reflection on that plane? Are we sure that integrand has odd symmetry through that plane? Make sure you can think all that through. That's all important stuff. Okay, if we're good on that, I'm going to proceed. I want to talk about some physical examples. The divergence there, the Gauss's divergence theorem is just off the charts important in engineering and physics, and probably, come to think of it, physical chemistry for if there's any chemistry majors in the crowd. There's plenty of places where it comes up. The engineering school has been very clear, with me at least, that this is the most important part of the course for them, and not even particularly close, right? They consider it just extremely important for students to understand vector calculus theorems of Gauss and Stokes. So this is on the short list of most important things in the course for engineering. All right, so there's various different physical examples. I'm going to start with a couple ones that I think are relatable. Not necessarily the most important ones, but the ones that are the most relatable. We'll get to the other ones probably on Monday. So here's my first example. It concerns a light bulb, and let's go ahead and make this a little LED light bulb. So it's got a teeny tiny little not a point light source, but a very small light source. Okay. At the center of this sphere, let's say. And what does a light source do? Well, it generates light, aka photons. A little physics for those of you who haven't seen that before. Light is communicated through little particles, surprisingly. And these little particles are called photons, and they all kind of flow together. If you have a single point light source, they flow together like a fluid, and thus the arrows here, all emanating outward from the point source. How are we doing? Does everybody believe it? All right. It's weird to think of that as a fluid, but well, it is. So Okay. Weird thing about this fluid. I mean, unlike water or air, fluids like that. What we have here is a situation where the fluid's literally being generated out of nothing, right? There's this thing in the middle, and photons just keep shooting out of it, as if out of nowhere. We're literally generating the fluid. Okay. Now that said, it's all spreading out and flowing away, and so even though we are generating fluid, the density of photons doesn't change over time, right? It's not like, if I were to look in this vicinity right here, if I were to, kind of put my hands around, make a little box over here and count the number of photons in there at any given instant. It's not like the number of photons, generating fluid. It's not like it begin collecting more and more and more, and eventually the whole box is just full of nothing but photons. Of course not. Right? Photons flow in, they flow out. So the photon density constant over time. But we're still generating fluid also consistently over time. Okie dokie. So let's talk about flux through this sphere, let's just say. I compute that flux. It's going to depend on the wattage of the bulb, right? And a certain amount of flux. Where's that flux coming from? I ask rhetorically. Well, it's sort of obvious where the flux is coming from. The flux is photons passing through that sphere. Where do the photons come from? They come from the bulb. They come from the little LED. That's the light. That's the thing that's generating the photons. Right? So the first observation I want to make, and it's hard to relate to when you're not thinking about a physical scenario, but remember I was trying to persuade this seemingly creepy idea that even though we measure flux on the boundary, it's actually coming from in the interior somewhere. Well, this is extremely relatable, I think, along those lines. Of course the photon flux measured on the boundary is actually coming from the interior. That's what the LED bulb does. It makes the photons. Okay, so I hope that's a persuasive point. Now let's try to talk about what would the divergence be at the center. And again, we can talk about the flux on this sphere out here. Now let me draw a really teeny tiny little small sphere here in the middle. What's the comparison between the flux on the outside sphere versus the flux on the inside sphere? Let me just ask that a different way. How many of the photons generated by the bulb go through the outer sphere? Well, all of them. How many of the photons generated by the bulb go through this inner sphere? All of them. Right? So, in the vicinity where the bulb is, we've got all of the flux happening on an extremely small amount of volume. Right? So, what's the flux per unit volume? We have a large flux over a small volume, and that means that where this point is here, where the bulb itself is, divergence is extremely high. As you remember, I also pointed out that divergence points to where the stuff is coming from, right? So sure, we've got flux on the outside, yeah. The divergence is going to tell us where on the inside specifically it's coming from. It's coming from the bulb. Divergence tells us that look how big the divergence is. Massive divergence. So that's where the stuff's coming from. By comparison, let's think about a point like, like over here. In that general vicinity, how much of the boundary flux, how much of the photons are coming from there? Well, none of them are coming from there. They're all coming from the bulb. This is just air. There's nothing coming from there. Now, to be fair, sure, there are photons that are coming out of that region, but those photons that come out of that region a billionth of a second prior had flowed into that region from somewhere else. So, again, not really from here. They're just passing through there. So, there are no photons coming from there, and again, divergence, I wanted the highlighter here. Sorry. Divergence points exactly to that. This is not a source of photons, therefore divergence is 0. Everybody buy it? Okay. Cool. All right, now that's just one physical sort of model, you might say, for the divergence theorem. Here's a different one. Oh, we're not going to have enough time for this different one. Okay, I tell you what, we're not going to have enough time to get far enough into this to be worth it. I'm sure I owe y'all some minutes, so I'm going to give y'all 2 minutes back. We're going to draw the line right there. We will pick up here on Monday. Y'all have a great weekend. See you on Monday.